Welcome everybody to the monthly edition of our COMSOC video seminar. We have two nice talks today by Mashbat and by Kiran. And we start with Mashbat, and I think the floor is yours. The usual format, 20 minutes of a presentation, 10 minutes discussion, 10 minutes break, and then we will have the second talk by Kiran. All right. So, Mashbat, we are happy to have you. Please, floor is yours.
Let me first share my screen. Can everyone see the screen? Hi. Thank you for everyone, and I would like to thank first the organizers for inviting me to give a talk here. I'm very honored for that. So this talk is titled Compatibility of Fairness and Nash Welfare under Subadditive Valuation. This is joint work with Siddharth Barman, and this was based on a talk that I gave at SODA 2026. Wait, hold on. The challenge of allocating resources fairly and efficiently is an important area of research. And if you think about it, the question of who gets what and why is a fundamental question that has important consequences across many aspects of our society. And specifically, this talk will be about fair allocation of indivisible items. So let me just go straight into the model. So you have set of n agents, set of m items, and each agent has a set valued valuation function where vi of s is a value that agent I has for subset of goods. And the central question in this field is, do fair and efficient allocations always exist? By the way, if anyone has any question, please ask me during the talk. So in this talk, I will be focusing on subadditive valuation. So each agent's valuation function is subadditive, which just means that value of a two set S union T is less than or equal to value of S plus value of T. So this generalizes the well-known additive, submodular, and XOS valuation. So it is the largest class of valuations that are called complement-free valuation. And throughout the talk, I will assume this very large generality of subadditive valuations. And an allocation is basically assignment of the items to people. So given an allocation, agent I is said to be envious of agent J if the value that agent I has for their own bundle is worse than value that agent I has for J's bundle, or in other words, I strictly prefers agent J's bundle to her own. So that's when we say agent I is envies agent J. And allocation is envy-free if everyone sort of weakly prefers their own bundle than everyone else. So no one strictly prefers any other agent's bundle. So this clearly may not exist because you can just have two agents and a single item such that the single item is, let's say, valid by both people. So no matter who the item goes, one agent will be always envious. So you have to relax this. And the popular relaxations of envy-freeness is envy-freeness up to one item. So this is an allocation is envy-free up to one good. If you can essentially just remove an item, if there exists an item from, let's say, J's bundle, such that I am no longer envious of them. And another sort of relaxation of envy-freeness is envy-freeness up to any good. Essentially, that says that between any two pair of agents, I and J, I doesn't envy J if you remove any good from J's bundle. So in other words, I doesn't envy any proper subset of some other agent's bundle. So these are the sort of the main fairness concepts studied in fair allocation of indivisible items. And this allocation you can see to be EF1, but not EFX. So let's say the skateboard and saxophone and painting. The Lisa gets the skateboard and the painting, and let's say the Bart gets the saxophone. Then Bart is envious of Lisa. This allocation is not, it's EF1 because Bart can remove the skateboard and not envy Lisa, but not EFX because there's another, if you assume additivity. And this was just to show that that these two are sort of quite different. And this one is EFX. Yeah, but the previous one was EF1, but not EFX. So these are the sort of the main fairness concepts studied in fair allocation of indivisible items. And on the other hand, economic efficiency is also an important axiom. So an allocation is Pareto optimal if no other allocation can improve some agent's outcome without worsening someone else. So for subadditive evaluations, it was shown that there exists an instance where every EF1 allocation fail Pareto optimality. So EF1 and Pareto optimality are not compatible with each other for subadditive evaluations. So for subadditive evaluations, therefore, efficiency of an allocation is measured by either approximate PO or Nash Social Welfare. And Nash Social Welfare just means it's a geometric mean of agents' values. And Karagiannis et al. Showed that for additive valuation, an allocation that maximizes this geometric mean of the agent's value or Nash Social Welfare allocation is envy-free up to one item. And beyond additive valuations, this is false. This is even violated even for gross substitute valuation, where Nash Social optimal allocation. So gross substitute is just the subclass of submodular valuation, and here you can construct instances where Nash Social Welfare optimal allocation fails EFK for any K. So if you give me K, then I can construct such instance. So these are far from true. And there was an open question in STOC 2023 by Garg, Husic, Lee, Végh, and Vondrák that's asked for submodular evaluations, does there exist an EF1 allocation that has high Nash Social Welfare? And sort of the main contribution of this work is that we resolve this above open problem even for a much more general class evaluation, which are subadditive evaluation. And another sort of an important open problem in this field is for submodular evaluations, does there exist an EF1 plus PO allocation? And we sort of all results imply progress on this problem. So let me sort of give you some highlight of our result. We show that for subadditive evaluation, there always exists an EF1 allocation that approximates optimum Nash Social Welfare to factor within 1/2. And this 1/2 factor is tight, meaning that there exists an class of instances where every EF1 allocation is basically at most kind of 1/2 plus epsilon Nash Social Welfare. And corollary of this result is that for subadditive evaluation, there always exists an allocation that is EF1 and 1/2 PO. Since one PO or a Pareto optimality cannot be achieved, you have to relax this. So we basically show that 1/2 EF1 and 1/2 PO is possible, and this is the first positive result on compatibility of exact EF1 and Pareto optimality. Although the Pareto optimality is in approximate sense, that goes beyond additive evaluation and actually holds all the way to subadditive evaluations. And we also have kind of a computational result, which says that given any allocation, given some allocation A star, we can compute in polynomial time an E-if-1 allocation that approximates the input allocations Nash Social Welfare to factor 1 over E to the 2 over E, which this is basically 1 over 2. This is very close to the best you can do. And we can achieve this in polynomial time. So in particular, if A star was Nash Social Welfare maximizing allocation, if that was given to me, then I can convert that in polynomial time to an E-if-1 allocation that is basically roughly half optimal. So many of the key ideas of the paper kind of lies in proving this theorem. And so let me kind of give high-level approach and the key sort of conceptual ideas behind how we prove this theorem, this 1 over E to the 2 over E approximation. So we can think of this A star as just a Nash welfare optimum allocation. This may not be fair. This may not be EFK for any K. So so we will start from that allocation. So this A star is this allocation. From A star, we construct union of n disjoint cycles. So basically, you look at the items that are in A1 star. So in the optimum allocation, what agent 1 get, you construct a cycle where each vertex is an item. And it doesn't matter how we construct it, as long as it's just a cycle. So you can basically order the items in any way you like. And you do the same for every agent, so all the way to n. And the algorithm will maintain a partial allocation that has the following two invariant, which is that these partial allocations are going to be E-if-1, and each partial allocation is a connected component on this graph. So it just means that these partial allocations will be paths on these cycles. So what we will do is that, and because it has to be connected, no one will actually get multiple paths. So everyone get a single path. So we initialize by giving sort of empty set for everyone. So no, empty set is connected, and that partial allocation is actually not only E-if-1, it's envy-free. And basically, we just have a single while loop that will look like the following. So let's sort of jump ahead, and you have a set of paths that are claimed by people. What does the while loop update do? So it looks at basically the graph, and you remove the paths that are claimed by people, and then the algorithm inside the while loop, it will look for an inclusion-wise minimal path that is envied by someone. So say this path is in a K star. So in this example, this Q, this red path is a minimum inclusion-wise minimal path that is envied by someone, and it's in, let's say, A2 star. So in general, it could be a K star. You check first does agent K envy this minimal path? If so, you give Q to that agent, and if agent K is not envious of this path, then you give it to any other envying agent. Right? So basically, and then that's basically just the update of the while loop. So essentially, we start with a bunch of paths, and so everyone started with empty path, and now the entire graph is feasible because the graph minus the path is this disjoint union of cycle. So you identify a minimal envied path, and then if that agent, depending on where this envied path comes in, you give sort of first choice to the agent who this agent K, or where Q belongs to. And you give first choice to them. If they don't want Q, you give it whoever else wants it. So that's basically the update rule, or algorithm. And basically, the algorithm is polynomial time because in this graph, there's only roughly m squared n choices of connected paths. and the algorithm sort of terminates, right? Because everyone else's value stays the same. Only one agent's path gets updated, and that agent's value increases. So if you kind of think of social welfare or Nash Social Welfare, it's kind of a Pareto improvement, right? Because everyone else remained the same, and one agent, at least one agent, strictly increase. So the algorithm is guaranteed to terminate. And there's and each time, the number of sort of iterations is at most m squared, and because there's only that many choices of paths. And so when the algorithm terminates, the allocation will be EF1. And since the algorithm terminated, no one, so you will have just a bunch of these paths that are selected, and no one will want an sort of unassigned path, unassigned connected component. And that if I look at, let's say, A2 or some AI star, if someone took from my set, my optimal set, that means that I don't envy them, because when they selected that path, I gave first choice to agent I, right? So all these properties are satisfied at termination. And so at termination, we have these three key properties. So let me kind of go into the analysis of the algorithm real quick. Basically, the analysis of the algorithm is you look at AI star, you can sort of decompose. So this will be set of claimed paths. So in this AI star, P1 is claimed by agent 1, P2 is claimed by agent 2, and P3 is claimed by agent 3. And then this Q2 and Q1 are these unassigned paths. So you can write, so you write SI as this assigned paths, and then LI are the unassigned paths. So you can clearly write AI star as this, union of assigned and unassigned paths. And you can use subadditivity, and along with these properties at termination to get this bound. And now, essentially, there's a very simple combinatorics observation where if no one took part from AI star, if no one claimed any path from there, then there can only be at most one unassigned path, right? So that means AI star. If SI, penalty of SI is 0, meaning that there's no claimed path in AI star, that means the entire thing is red. So LI is 1. If some people took some paths from AI star, then the number of unassigned paths is at most cardinality of SI, number of assigned paths, because between any two assigned paths, so any two paths that I gave to agent, there can only be at most one connected component between them, right? That is unassigned. So therefore, this inequality must hold. And since everyone can only claim one path, this also holds. So because everyone's path is connected and we have this union cycle, you have also this inequality. And then essentially the analysis comes from now just kind of looking at this inequality and applying arithmetic geometric mean inequality and doing some calculus to get this e to the 2 over e bound. Now basically what this means is that when the algorithm terminates, this partial allocation approximates optimum Nash Social Welfare to factor e to the 2 over e. And now we actually haven't allocated all the item, and we can just complete this partial allocation, which are just these paths, item paths. You can complete this by NV cycle elimination. Basically, you can without hurting the Nash Social Welfare approximation guarantee. And so we have further results. Basically, you can replace this disjoint union of cycles by disjoint union of cliques, and we get that. And running exactly the same algorithm, you can get that there exists a partial allocation, partial EFX allocation, that approximates Nash to factor within 1/2. And this holds for subadditive valuations. And this is tight even for additive valuation, by the way. This 1/2 factor is tight even for additive valuations. And we also have applications to fair division with constraints. Since I don't have too much time, I will sort of briefly go over this. Basically, we are, in fair division, constraints are specified by a set family, and we have a very sort of, as long as the set family is downward closed, meaning that if A is in the set family and B is subset of A, then B is in the set family. So this is what it's called downward closed. And as long as this feasibility constraint holds, so this captures matroid constraint and connectivity constraints, we can essentially get the same thing where we can get a partial allocation that is EFX and approximates the optimum Nash social welfare allocation, optimum among all feasible allocation and to factor 1/2. And in the last 2 minutes, I want to give a summary and future direction. So we should
1 minute. 1 minute,
yeah,
not 2.
yeah. So there's always, and we showed that there's always an EF1 allocation with high Nash social welfare for subadditive valuations. And we showed that you can also do the same thing with partial EFX and high Nash social welfare with arbitrary downward close constraint. And we have this open problem. We know that for submodular evaluation that it could, maybe the factor could be improved, and instead of 1/2 or instead of 2, maybe you can improve it to e to the 1/e. So we know that you can't do better than e to the 1/e, but maybe you can do better than 2. So what is the right bound for submodular evaluation, and other applications of this algorithmic framework would be very interesting. So some similar ideas have been used to subsequent of this work applied to divisible item division. So future sort of directions of how to apply this algorithmic idea would be also interesting. And that's all. Thank you very much.
All right, thank you very much, Mashbat. So let's give a round of applause to the nice talk. And we do have a question here. Vishwa, you have a question. Do you want to pose it? You have it in the chat so far, but do you want to pose it orally?
I think Siddharth, I was just thinking of removing some champion cycles to boost this EFX and half NSW to also get additional n-1 or n-2 charity.
Yes, you can do that. Yeah, you can do that. So you can get n-1 charity by just directly putting that as an input to this bounded charity algorithm, because they only do Pareto improvements. So yes, and then I'm sure you can also do n-2 as well. Yeah, because if it's Pareto improvement, you can just put this final allocation as an input to their algorithm, and then you can also get bounded charity.
Very nice.
Okay.
Thank you.
Okay, Dominique, you have a question.
Thanks for the talk. Suppose I care about approximate Pareto optimality, but not approximate Nash social welfare. Then it's a bit surprising to me that you get the best known result, maybe the first known results for the approximate PO through Nash social welfare and not, for example, through utilitarian social welfare. Can you give a bit of intuition for that?
Yeah, so this was also kind of a surprise for us as well. So the intuition is that, like, at least for me, comes from the additive valuation, where for additive valuation, Nash social welfare optimum is exactly PO and EF1. And so there's a sequence of works on price of fairness result. Basically, you can also, one way of interpreting our result would be like you look at the sort of the best social welfare maximizing allocation divided by the best fair EF1 fair allocation. It was shown that even for subadditive valuation, For social welfare, it's root n for skilled and for unskilled. So essentially, what we show is that price of fairness is 2 for subadditive valuation for Nash Social Welfare. And I think Nash Social Welfare sort of just gives you a really good way of achieving Pareto optimality that sort of isn't captured by, let's say, utilitarian social welfare or yeah. So it's somehow there seems to be if you want PO, you should look at, and fairness, you should look at Nash Social Welfare.
May I add one question? I mean, to this. What I find surprising is that if you move away from additive to general sub-additive, you go to a factor of 1/2, which seems to be right from 1 to 1/2, which is a large jump, I would say, downward. So do you have any idea what kind of sub-additivity do you need in order to achieve? I mean, you said the bound is tight, right?
Yeah.
So do you need a lot of non-additivity, or have you thought about approximation results in terms of how much additivity do you need to converge again to the one? You understand my question?
Yeah, I understand. So I think this bad example is very sort of carefully constructed. It's very subadditive. You have marginal 0 for one person, but then this gives us positive marginal, and then you get this chain. And so it's very carefully constructed that heavily uses subadditivity. That's the 1/2. And if you sort of relax that, even for submodular, I suspect that you can do better. And if you go down even to gross substitute, I mean, so we know that you can't do better for a gross substitute e to the 1 over e, but okay. You that kind of looks additive. So right, you can, I mean, that's debatable, but if you believe that gross substitute valuations are very similar to additive, then it's already pretty bad. E to the 1 over e is I think 1.4 something, or so it's already quite bad. So it somehow jumps quite suddenly, if you will.
All right. Okay. All right. Very interesting. So, Dominic,
I have another question. Can you remind me, do you need to do the NV graph Lipton and al step to get the 1/2, or could you stop before?
Yeah, so we can just stop this NV graph elimination, NV cycle elimination part is just to get a complete allocation. Actually, you can just stop right there and then. It's already giving you 1/2 approximation. And so it is kind of surprising, that you
suppose
don't
we stop
allocate.
there. Sorry.
Suppose
we stop there. Then the allocation you make compared to your original allocation has quite a lot of structure, right? Because you're not allowed to merge items from 2 original separate bundles.
Yeah.
Not quite sure what my question is, but does this come with a cost, or is this kind of idea, does it show up elsewhere in fair division where this is not actually necessary?
So the surprising part is that 1/2 is tight. So even though we're doing this kind of very naive thing, right, it's just optimal. So you construct a bad example in some ways that kind of mimics it, that the order set's marginal values are sort of 0 to you or whatnot. So even though it seems ad hoc, this 1/2 just is tight and you can't really do better, and it's kind of a surprise that this very simple sort of iterative local thing just gives you optimum.
All right. Okay. So any other question, comment? Okay. If not, so we'd like to thank the speaker again. Thanks. Welcome back from the break. Our second speaker is Kiran Tomlinson, and he will talk about instant runoff voting. Let's see what you have to say. Floor is yours. Thanks for joining.
Thank you very much for the invitation, and let me just share my slides here. Okay, great. All right. Yeah, thanks again. My name is Kiran. I'm at Microsoft Research right now, but until recently, I was a grad student at Cornell University. And this is joint work with Johan Ugander at Yale and John Kleinberg at Cornell. I presented this work recently at AAAI in Singapore, but in case you happened to be there, I've added a few things, so hopefully there will be some new information for you. Right, so the title of this talk is Exclusion Zones of Instant Runoff Voting, and you'll shortly know what those are. The main question that we're interested in this work is, given some distribution of voters in a metric space, where the metric space is describing their preferences, their ideological positions, are there regions in that metric space that a particular voting algorithm will favor? For example, if you've got a one-dimensional ideological spectrum from liberal to conservative, and voters are kind of clustered towards the center, will a particular voting system consistently favor moderates close to the median? Or are there voting systems that are more likely to elect extreme candidates? You might have higher dimensional preferences, like this two-dimensional distribution. And there, again, you can ask, in what region of the space will a voting system tend to elect candidates? This is a little bit different from questions given a particular profile over a fixed set of candidates. So here we're interested in any possible election that could play out in this metric space. So my candidates could be any subset of points. My voters are fixed, and I want to know, for any election, will some particular position be favored? I'm going to be focusing on instant runoff voting in particular, but some of the ideas that we develop could apply to any voting system in a metric space. But in case you're not familiar with IRV, I'll quickly run through it. So the idea of IRV is that we have rankings from each voter over the candidates, and we're going to repeatedly eliminate whoever has the fewest first place votes. So the current plurality loser is eliminated. For example, here, apple and grape are the tied plurality losers. So let's break the tie arbitrarily, eliminate grapes, then reallocate. Now apples are in last place, we eliminate apple, and then finally strawberries are eliminated. So lemon is the IRV winner. But notice that strawberry was the plurality winner, and it doesn't matter, in this case, it doesn't matter in what order we eliminated apples and grapes, we'd still get the same outcome, but in some cases, these ties will matter. You might know IRV by one of its many other names, but I'll call it IRV. A couple of years ago, the same set of co-authors and I showed a kind of surprisingly simple result about IRV in one dimension, that it always favors candidates in a region around the median voter, at least if voters are symmetrically distributed. And we've formalized this using this idea of an exclusion zone. So this is a really key definition for the talk, so I'll go over it carefully. So the idea behind an exclusion zone is that we have some fixed distribution of voters in a metric space, and an exclusion zone is some set S of points in the metric space where the winner is guaranteed to come from S unless no candidate runs in S. So this is a statement about all possible elections, regardless of how I pick my candidates. As long as at least one of them belongs to S, then the winner of the election will be an S. You might say, okay, you can trivially satisfy this if you pick S to be the entire space. So we're going to be interested in small exclusion zones. And we showed, among other things, that if you have maybe the simplest one-dimensional setup you could have, uniform voters distributed over the unit interval, then IRV will only elect candidates from 1/6, 5/6. So the extremes cannot win under IRV unless all candidates are extreme. And the argument is simplest when voters are uniformly distributed, but this holds for any symmetric unimodal distribution, like the one on the left, if you assume it's symmetric, and even some kind of polarized distributions. Let me run through the proof since it's not very long. The idea is that IRV proceeds by eliminating candidates one at a time until you only have one candidate remaining. So let's say to start out with, we're going to have a bunch of candidates, could be a small number, could be a large number, distributed somehow over the interval. Candidates are going to be eliminated one at a time. So at some point, there will only be one candidate remaining in the middle 2/3 of the interval, in that 1,656 interval. And once there is only one candidate remaining in that interval, then the point is that the candidate to their left and the candidate to their right are far apart. And therefore, that middle candidate can no longer be squeezed out. They've got now at least 1/3 of the vote, or strictly more than 1/3 of the vote if they're the last remaining candidate in that interval with uniform voters, since they're getting half the size of the interval they belong to. And with candidates on their left and the right, there are at least 3 voters, so they can't be eliminated with more than 1/3 of the vote. And this continues to be true. X can't be eliminated until all of the candidates on one side are gone, and then X is the winner. And if you try this argument with any smaller interval, this won't work. So 1,656 is the smallest exclusion zone in this one-dimensional setting. So for this work, we wanted to broaden this idea and take this definition and see how far we could carry it. What happens in other metric spaces? Are there more general properties of exclusion zones? So if you think about this for a few minutes, you might come to the following conclusion, that if you have 2 different exclusion zones of a voting system with a particular metric space and voter distribution, then one of them must be a subset of the other. And this is very easy to show if you assume by contradiction that this is not true, that you have 2 points that are in one but not the other, and then you think about an election between those candidates at those 2 points. And if one of them wins, then the other one is an exclusion zone. So one thing that kind of immediately follows from this nesting is that I can take this set of all exclusion zones of a metric space and take their intersection. They're all nested. So the intersection of all of them is like the kind of the shared portion of the metric space that all the exclusion zones have. And so we call this the minimal exclusion zone. It also satisfies the definition. So what you have then is this nesting from the set of all positions, which we call the trivial exclusion zone, all the way down to the minimal one. And in IRV in one dimension, the trivial exclusion zone is the whole interval, and then the minimal exclusion zone is that 1,656 interval. And indeed, if you take any symmetric interval between 1,656 and the unit interval, it also satisfies the definition. So let's think about a different voting system for a second. Let's say we're considering any Condorcet method in 1D, since we know that they're very well behaved, since whoever's closest to the median will win. And there you again have these nested intervals, but with Condorcet methods, any symmetric interval will satisfy this property, that if a candidate belongs to that interval, then the winner belongs to that interval. And this is just because the closest candidate to the center is winning, and these symmetric intervals are exactly the sets that include all points closer to the center than points in the interval. And then the singleton 1/2 is the minimal exclusion zone of a Condorcet method. So this is what the nesting looks like. And I kind of want to argue that the set of exclusion zones of Condorcet methods in 1D captures the median voter theorem. That if I only told you, here is a set of subsets of the metric space that have the property that the winner always belongs to these sets, then you could kind of deduce the median voter theorem from this nesting. So we thought that was kind of nice. And I'm interested if there's any nice properties that you can understand about a voting system by looking at its collection of exclusion zones in other settings. Okay, now let me give you one more definition that'll be useful for our results. And these are Condorcet and anti-Condorcet positions. So this is going to be related to Condorcet winners, but kind of subtly different. So the idea is that if we have, again, a metric space and a voter distribution, then I'm going to call a point in that metric space a Condorcet position if for any other point in the metric space, at least half of the voters are closer to X. So this means that in any election that I could pick, including the Condorcet position would be a Condorcet winner. but it's a property of the metric space and the voter distribution rather than a particular profile. This is also called, in the literature on voting games, this is also called the core. And then an anti-Condorcet position is the opposite. It's a point that's majority dispreferred to every other point. So in 1D, the median is a Condorcet position, and the endpoints are anti-Condorcet positions. And just like the first exclusion zone property was pretty easy to prove, it's also easy to prove that if you have any reasonable voting rule, then Condorcet positions are always going to be in the minimal exclusion zone. If they weren't, then you would have a counterexample, because the Condorcet position defeats any other point. And if an exclusion zone contains a weak anti-Condorcet position, then that exclusion zone must be trivial. It must contain every point. Otherwise, you would have a counterexample to it being an exclusion zone again, because that position is defeated by any other point. And this holds for any voting rule that selects the majority winner when there are only two candidates, which I think hard to think of a reasonable voting rule that doesn't satisfy that. So given these facts, we can put together a proof technique for showing that in general settings, the minimal exclusion zone is trivial. That is that it's we have this proof technique for showing that there don't exist interesting exclusion zones. And we're going to use one more fact about exclusion zones, which is that if I have some exclusion zone S, and I can construct some election that has some candidate in an S, but a different candidate wins, then that other the position of that other candidate must also be an S. And this again just follows from the definition. So now here's our proof technique. We call it the Condorcet chain lemma. The idea is that we're going to try to find a sequence of elections, of candidate configurations, with winners W1 through, that should be Wn, with the following properties. So the first configuration has a Condorcet position, but a different candidate wins. Then each next configuration includes the winner of the previous election, but is won by some different candidate. And finally, the winner of the last configuration is an anti-Condorcet position. If you can find such a configuration satisfying these properties, then there are no non-trivial exclusion zones. Or another way of saying that is that the minimal exclusion zone is trivial. And this just follows from chaining together the facts that I've introduced so far. Okay, so now I think we have all the tools that we need to dive into our results. The first thing that we were interested in is whether this one-dimensional exclusion zone for IRV extended to higher dimensions. This was maybe the main open question from that earlier work. And the first thing that we showed is that the square, as soon as we go from one dimension to two dimensions, and again, we have uniform voters, there's no non-trivial IRV exclusion zone. And we proved this exactly using the Condorcet chain lemma. So this is a sequence of 4 candidate configurations, starting from one that has a strong Condorcet position. So with uniform voters, the center of the square defeats any other point in a pairwise contest. But the first configuration is won by a different candidate. And then the winner of that first configuration, W1, loses in configuration C2. And the whole point of this configuration is to make progress towards a corner. And the corners here are anti-Condorcet positions. So just establishing the sequence of configurations show that there is no set of points in the square that satisfies the exclusion zone properties. And in fact, you can generalize this a lot. You can show this not just for squares, but also for rectangles, not just for L2 voters, but if voters have L1 preferences. I suspect this is also true for any other LP. But with this proof technique, you kind of have to make one construction per metric. So it would be, unless we had some clever way of handling other metrics, just have results for L1 and L2. And this generalizes to higher dimensions. And the argument for generalizing to higher dimensions is just that I can run elections in 2-dimensional subspaces of any higher dimensional hyperrectangle. and through the sequence of configurations, make progress towards a corner, one dimension at a time. So all I need are these two-dimensional configurations, and as soon as I have those, then I can construct the sequence in any higher dimension. And just to quickly show the idea of the sequence with rectangles is that, again, starting at the center, I can make progress towards the edge by having candidates that kind of move slightly to one side, but not enough that they expose too much of the voters to the center candidate C. And then once in order W, where W is the ratio of the length of the rectangle to its height, we can make it to the edge, and then we start slowly making progress towards the corners. And for L1, the construction is pretty similar. So does this mean that exclusion zones were just a one-dimensional phenomenon? We also show the answer is no. So if you consider uniform voters over this slightly funny shape, then the shaded region S is an exclusion zone with uniform L1 voters. I suspect that there may be more natural voting distributions that have exclusion zones for IRV in 2 dimensions, but it's I don't know of any. So if anyone comes up with one, I'd love to see it. The problem with hyperrectangles is that because they have so many symmetries, there are too many directions from which you can squeeze out candidates and make progress towards an anti-Condorcet position. So now I want to shift gears from Euclidean space to talking about different preferences. So here we'll think about voting on with a graph metric. So now I have a graph where nodes represent voters, some subset of the nodes are running for office, and voters prefer candidates closer to them in the graph by path distance. So for example, you could think about the graph representing family ties. Like this is the graph of 15th century marriages between important families in Florence. And you might think that if your family is closely linked to another, that you would support them in the local government. Or if you're in a karate club and the club is splintering into factions, you need to vote for who's going to be the winner, then maybe who you are friends with, who you train with will influence who you vote for. And since there are a lot of ties in graphs, it's very often that a node is equidistant from 2 others. We'll use split IRV to handle those ties. So we think of each node having vote share 1, and in each plurality round, they're splitting that vote share among equidistant candidates. Just by doing an exhaustive computer search, you can find what the minimal exclusion zones of some small graphs look like. So here I've shaded the minimal IRV exclusion zones in blue. And some instances kind of generalize or are approximations to some of the Euclidean results. So this 1/6, 5/6 interval shows up in the path graph, but with some rounding. But here we can have kind of more interesting topologies. We can have cycles. More generally, you might want to know, if I have a graph, what is its minimal exclusion zone? Or if I have some candidate set of nodes, is that an IRV exclusion zone of the graph? So we think about this as a decision problem where we're given a set of nodes and we want to check if it's an IRV exclusion zone. Unfortunately, even checking IRV exclusion zones in graphs is computationally hard. We do have an approximation algorithm where we can find nodes or sets of nodes that are likely approximate exclusion zones. It's a randomized algorithm, and it finds a subset of nodes that is guaranteed to be a subset of the minimal exclusion zone. And what it means for something to be an approximate exclusion zone is that under uniformly sampled elections from the graph, it behaves like an exclusion zone. So most of the time. So under at least a 1-epsilon fraction of these random samplings, the winner will always belong to S. And then luckily these graphs were small enough that we could identify their minimal IRV exclusion zones. But if they were any larger, the karate club graph is about as large as we can handle before running into computational hardness. And just something in these graphs is that in the Florentine marriage network, the Medici family is a Condorcet position. And they, in fact, ended up ruling Florence in the 15th century. And in the Karate Club graph, the instructor, Mr. He, is also a Condorcet node. So I think these are nice examples of how voting theory can help you think about social networks. So in our paper, we've got more details about the algorithms. We've got some exact characterizations of the minimal IRV exclusion zones for some families of graphs, and then some more experiments on real-world networks of our approximation algorithm. I also wanted to mention some kind of related ideas. So I mentioned that the Condorcet position is also known as the core in this literature on voting games. So that's another literature where this idea of having a metric space and trying to think about what regions in that metric space are likely to end up dominating has come up. There, it's been in the context of some strategic game or some iterated game where candidates are choosing their positions, or maybe they're not doing it optimally, but there's some kind of dynamics going on. Here, I think it's interesting to think about this question without any game playing, without any dynamics, just thinking, I have a voting system, I have a metric space, I have some set of voters, what regions are favored? There's also some related work about kind of generalizing the idea of Condorcet winners to sets. There's this nice paper recently introducing Condorcet winning sets, where you think about a collection of candidates that collectively satisfy some version of the Condorcet criterion. So I guess those are some other places to look if you want to think about sets of candidates or positions that are in some sense favored or preferred. I think there are a bunch of open questions here. We know very little about exclusion zones for other voting rules in Euclidean space with a graph metric. You could even think about other metric spaces. These were just kind of the first two that occurred to us. And I would really like some more natural voter distribution with non-trivial IRV exclusion zones in higher dimensions, because this two-dimensional shape just with L1 voter distributions is maybe not too satisfying. So thank you very much for your attention, and yeah, happy to take questions.
Yeah. So thanks a lot for the thought-provoking talk. Give a round of applause here. And before I get to the more detailed question already in the chat, let me ask, please, two general questions. My first question is, why do you call it exclusion zones? Because you're not excluding the elements from the zone, but those that are outside it. That's my first question. And the second question is, I'm thinking the entire talk, I was thinking, well, is it now good for a voting rule to have non-trivial exclusion zones, or what is the normative status of the analysis? I was wondering about that. Have you any thoughts for this? And yeah, sorry for posing these two questions first, and then we go to the questions in the chat.
Yeah, I think these are two great questions. So I'm happy to start out with these. First of all, with the name, I totally agree. It is a maybe slightly awkward name. We kind of introduced this in the moderating effect IRV paper a few years ago without thinking about it too much, because it was just like some definition that we needed for the proof, and it wasn't our main focus. And then we realized that we wanted to think about them more, and had several discussions like, should we rename them? I gave a talk at the joint mathematics meetings a year ago or so, and for that talk, I changed the name to winning sets because I thought that was a clearer term. And then this paper about Condorcet winning sets came out, and then we thought, well, maybe that's too similar. And then when we were writing the paper, we thought, okay, maybe it's not the clearest name, but we already have one paper that calls them exclusion zones, so let's just stick with it and answer these questions after the talk. The idea was that as soon as one candidate belongs to the set, that excludes everyone else. That was the initial motivation. We didn't think about it too much, and so maybe could have come up with a better name. In terms of the normative part of the question, my sense is that it's good to have small exclusion zones if you believe that, that in one dimension, the Condorcet winner being the median voter being elected is a good thing, because in some sense, it's it's some good compromise. I'm sure you could come up with, like, a voting system could have an exclusion zone that is bad, that, like, the exclusion zone of a voting system in one dimension could have been the extreme points. And if you could come up with some maybe antagonistic voting rule that elects, like, candidates with the worst social welfare. So maybe in those situations it would be bad, but I think it's likely that reasonable voting rules will tend to have exclusion zones that are something like around the median position. They always include the Condorcet node, so the Condorcet position, so there's at least that property.
Well, when I think about it, perhaps it's not only the size of the exclusion zones that is important, but also the location, right? So it matters where these exclusion zones are located, probably. Okay, but anyway, I think this is an interesting question to study. All right, okay, thanks. So let's go to other questions. So there's Drew who has a question. Drew, you want to just pose the question, or should I read it? Drew, are you there? Okay, so I read it. Do you think that the 2D no non-trivial exclusion zone result would also work for, say, a 2D circle? Do you think a space must be non-convex in order to have a non-trivial exclusion zone? Any thoughts?
So for the circle, yes, I'm pretty sure you can construct a similar sequence of configurations for the circle. In terms of whether it must be non-convex, with uniform voters in higher dimensional Euclidean space, I think that's possible, because you can, it feels like you can kind of do this three candidate configuration where you have two that are slightly to the side and make progress outward from the center in any direction. So I think that might be true.
All right, okay. And then Bill has a question. What can you say about exclusion zones when you know voters' position only approximately in Euclidean space?
This is kind of a robust.
Yeah, Bill, you can speak yourself, right?
I can, but you did it well.
Okay, thanks.
Yeah, this is a good question. I think it depends exactly how you define your approximate knowledge of voter positions. Maybe the obvious thing is that if, regardless of what voter distribution or set of positions you allow, as long as there is a shared Condorcet position among all of those, the possible voter positions, then you know that's in the minimal exclusion zone. If you allow enough variance that you start breaking properties like that, then I imagine that you would have different exclusion zones. You can probably, like, in one dimension, at least with the 1.656 interval, I'm sure you could show something like, if you perturb the distribution a little bit, then that set is kind of stable, that maybe the boundaries move a little bit, but I would expect there to still be that exclusion zone.
Yeah, I guess I'm just suggesting in that case that you add some robustness results to the results you have.
Right. Yeah, this is a good question. And maybe we could have something like that with approximate exclusion zones. Like if you have some fixed voter distribution and you have an exclusion zone and you perturb it, then maybe you can at least show that what you have is still an approximate exclusion zone.
here's another interesting question, I think. Do you think, Sanjukta says in the chat, do you think that the size of the exclusion zones can be connected to strategy proofness? I think that's an interesting one to think about, because yeah, the intuition would be exactly that. I mean, given this one-dimensional median result, right? That small one-point exclusion zones should be somehow related to strategy proofness. Do you have any thoughts?
Yeah, it's totally possible. I don't know of any connection immediately. But it also feels like if you have a singleton exclusion zone, that's a very strong special case. And maybe in that setting you would have some kind of stronger statement you could make. But if you only have, like with IRV, this larger interval, it still feels like if you have candidates within the exclusion zone, now that the exclusion zone property says nothing about what's going to happen, about what the outcome is going to be. And so you have quite a lot of flexibility there. It's also maybe a bit hard to think about how the kind of winner being guaranteed to be in the set relates to strategies of voters. Maybe you could say something about the strategy of a voter that is inside or outside of this exclusion zone.
Yeah, so I asked this question because as Clement said that if it is in the one dimension and then you just have this median voter, then it seems that it is difficult for the other voters to manipulate the outcome. So yeah, it's not very clear, but I was thinking if you have some intuition about it.
Yeah, I don't have strong intuition about strategy proofness as it relates to exclusion zones, but that's an interesting question. I guess maybe one other thing to say is that strategy proofness is usually just a property of the voting system, and exclusion zones are a property of the voting system plus a distribution of voters in a metric space. So you could have fixing a voting rule have totally different exclusion zones as you vary the voter distribution. But I guess you could define strategy proofness of a voter with respect to a population, but I feel like the definitions I'm more familiar with are for any possible profile.
Right.
All right. I think we can have one more question. Mashbat, you have a question here in the chat. Do you want to...
I was just kind of, if you just have a, kind of going back to Sanjukta's question, if you just have a circle and the agents are uniformly distributed on the circle, there's no non-trivial, everything must be, like there's no single point, right? That's an exclusion zone. And
for
yet
IRV, right.
So there's, I think you can still do some type of median voter thing there, right? You look at, like I'm just not sure. Like I don't see how that relates to strategy proofness. Basically, that I don't see any, because on a circle, there's no single point or there's no non-trivial exclusion zone, and yet there are strategy proof rules there.
What kind of strategy proof rules are there? I'm not aware of any interesting strategy proof rules.
That is only for single peak preferences, right? So if you have some distribution, it will, I don't know if does that exist. Is there a guarantee of existence of strategy proof rule for a cycle?
Yeah, for I think single peaked, I believe so. Yeah.
No. But satisfied tends to work even for circles.
Yeah.
It does. Okay.
Yeah. No, you don't have a strategy proof rule, even for single peak preferences. All right. Anyway, so it seems to be an inspiring talk. So, but we have to close. I would like to announce. So, thanks again for both speakers for very nice presentations.